Welcome everyone. In this video we will analyze an Atwood machine. So what is an Atwood machine? It is actually Atwood's machine, I think. Atwood's machine, and this Atwood is not Margaret Atwood. I think the name is George Atwood. He's as far as I know, an English physicist, engineer who lived in around 17th century, 18th century, I think, or maybe 19th. I'm not sure, but around that time. So yeah, basically, this is not Margaret Atwood, which you probably guessed, because she is an author. Alright, what is an Atwood's machine? It is basically a pulley system. So we will have, let's say we have the wall, not the wall, I mean the ceiling, and then there is this pulley. There will be masses hanging from both sides. We have M1 and we have M2. Okay? And for the sake of simplicity, we are going to assume that there is no any frictional forces involved, there is no air resistance, the pulley is frictionless, the rope is massless. We make nearly all the possible assumptions. And you don't need to make these assumptions, but we're just interested in the ideal pulley. Okay? You can do this problem with friction if you are given the frictional value. It isn't that complicated compared to this one, but we simply are not interested in doing that for this video. So we have these two masses, and let's say that, it doesn't matter that much, but let's say that M1 is heavier. So I'm going to say that M1 is greater than M2. So which way will this, if we release this from rest, okay, I'm not giving any initial velocity. If we release this, the M1 will move upwards and M2 will move downwards, right? Because, well, that's wrong basically. What did I say? Excuse me. Obviously, M1 will move downwards. It is heavier. M1 will move downwards and M2 will move upwards. This is common knowledge, I think, but we don't even need to trust to our common knowledge. We will see that this is in fact what happens. So let's not even bother with this, okay? Let's say that there is acceleration 1 and I show it as upwards. You see that I showed the acceleration 1 as upwards, even though I think it will be downwards because M1 is heavier. But trust me, the math will show the result. And well, let's say that A2, this time I know that A2 will be downwards though, right? A2 will be downwards. According to my calculation, basically. And so what can we say? Well, let's write the force equations now. Let's first show the forces. So there is M1G, and there is the tension pulling it up. Then there is M2G, and then there is the tension pulling it up. If I were to choose the upward direction as the positive and the downward direction as the negative direction, then what can I write? I can say for the first one, the net force is going to be T minus M1G, and it will equal M1A1, right? And then for the other one, again, it will be T minus M2G equaling M2A2. And please don't get confused here. Maybe drawing the arrows might confuse you on this, but when I write A2 here, I am referring to the acceleration itself. It is a vector quantity directly. So that's why I don't put a negative in front, because if you were to look at the picture, you would say, hey, you showed A2 as downwards. Why don't you put the negative sign? Well, I don't put the negative sign because I don't even want to think about it as a scalar quantity. I am interested in it as a vector, okay? We could even erase these accelerations, right? Let's say that we couldn't even imagine which direction they were. We could still write this. This is Newton's law, Newton's second law, okay? That's why I don't write it like a negative. And as you can see, we don't even have the accelerations now. So what can we do? Well, a good thing here is that, and this is the thing that you need to be able to figure out, basically, no matter the direction of the acceleration for each mass, they will be accelerating in the opposite direction. This is something that you need to be able to come up with. And because that happens because the length of the rope should stay the same, right? You have this rope, and if mass 1 is moving downwards, the rope is getting longer on this side, so it should be getting shorter on this side, and for it to be getting shorter on the right side, the second mass should be moving upward, which is the opposite direction. So the key thing here is, which you probably can sense, it is that A1 equals negative A2. So in fact, for this one, let's say, I can write negative A1. I substituted for A2. Okay? And so if I were to subtract these two equations so that I get rid of the tension, we will have then M2G minus M1G equaling M1 plus M2A1. And so if we solve for A1, it's going to be that it is equal to M2 minus M1 over M1 plus M2, and then you have the gravitational acceleration. And let's see if this makes sense. So this is saying basically, if you look at this, I mean, don't even bother with this condition, okay? Well, maybe if I need to even erase it. It was for the sake of arguments at the beginning, but we don't need it anymore. So if you look at this, if M2 is heavier than M1, this is going to be positive. In that case, M2 would be moving downwards and M1 would be moving upwards. And that is exactly what we see, because this is positive and the acceleration ends up being in the positive direction. If, however, M1 minus M2 is negative, meaning that M1 is heavier, then what would happen is, since M1 is heavier, it would move downwards and M2 would move upwards. If M1 is moving downwards, if it is accelerating downwards, then the acceleration should be negative, and it is in fact negative. So this makes sense. And using this, we can also figure out the tension involved, and after that, there is pretty much nothing left for us to do with this simple Atwood machine, because, as I said, we don't have any frictional forces. So yeah, this is basically what we can do. We find the acceleration and we also find the tension. And of course, without needless to say, the acceleration for the second mass is just going to be the opposite of this, as we discussed it here. So what is the tension? Tension is equal to, I am going to use this equation and I will add M1G to both sides. So we will have M1G plus M1A and A1, of course. This is going to be equal to then M1G plus M1. I'm going to substitute the acceleration value that we just found. M2 and then G. Well, if we were to combine all of these under one common denominator, so I'm going to multiply the first, I'm going to multiply the first term by M1 plus M2. Of course, I can't just multiply it. It will be like this, M1 plus M2. And I multiply the top as well, so it is M1 squared plus M1 M2. Then we have plus M1 M2 minus M1 squared over M1 plus M2. I also took the G out, like this. So we can now add these two fractions. M1 squares will simplify. We have M1 M2 plus M1 M2. That gives you 2 M1 M2. So it's going to be 2 M1 M2 divided by M1 plus M2. Then the gravitational field strength, the gravitational acceleration. And this is the value for the acceleration. Of course, this is just the magnitude of the acceleration. I mean, well, it doesn't really matter though, does it? I mean, because for both of the masses, it is acting upwards. So yeah, this kind of also has the direction in it, because due to the fact that it is positive. But I mean, yeah, never mind. This is the value of it. And if anyone were to ask you what is the direction of the tension acting on each masses, you're going to say that it is upwards because the tension is a pulling force. But for example, for the pulley, if we were interested in the pulley's motion as well, maybe we were given its mass as well, then the tension would be pulling it down, okay? So the tension is not always upwards for the rope. It is just that it is pulling each mass up. And its value is this. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. If you want to see further videos like this, please make sure to subscribe. And this is it. I hope to see you in another video. Until then, take care.